Here we're going to look at a really neat proof of the Pythagorean theorem that finishes everything off with a combinatorial argument. And in fact, this comes from a Math Magazine article by this author called A Combinatorial Proof of the Pythagorean Theorem. So let's get our setup first. So here we've got a right triangle with side lengths A and B and a hypotenuse length C. I've put this angle here as theta. Now let's observe the Pythagorean theorem, a squared plus b squared is c squared, is equivalent to a over c squared plus b over c squared equals 1, which is in turn equivalent to sine squared plus cosine squared is 1, where sine is a over c and cosine is b over c. So we haven't done anything fancy yet. And what we'll end up doing is finding the Taylor series for sine and cosine, but that means we'll need the derivative of sine and cosine. But you might think you need the Pythagorean theorem to prove the derivative of sine and cosine, but in fact you don't. All you need is the angle sum formula, which can be done without the Pythagorean theorem, simply with a geometric argument, and that's what we're going to do right now. So here's my setup. I've got this triangle with angle measure alpha plus beta, and this triangle with the big angle will have a point there which we'll call O, and then a point up here which we'll call P, and then we'll call that point there B. So OBP is our triangle with that angle alpha plus beta. Then we put some more points into this picture, like a point A here. And then next, a point R right here. So notice that's the point here, not the one right underneath it, just to be careful. And then we'll put a point Q right here. Okay, nice. Now I'd like to make the following observation, and that is that the sine of beta can be calculated via this triangle right here. We have OQP. That's because this angle OQP is a right angle. And in fact, well, what is it going to be? Well, what is opposite the right angle here? And that is OP. So that's going to be on the denominator. I'll put PO. And then what's opposite the angle? Well, that's going to be QP or PQ. So that's sine of beta. And then using the same triangle, we can pretty easily calculate cosine of beta as OQ over PO. Well, of course, it's going to be over the same denominator. Now, we can do the same kind of thing for our cosine of alpha and our sine of alpha, and that's simply going to use this triangle down here, this one with angle alpha. So let's see, that's going to give us the sine of alpha is equal to, well, it's going to be AQ over OQ. So let's write that down, AQ over OQ. And then the the cosine of alpha, well, that's going to be AO over OQ by the same argument. Now, here's another thing we need to do. We need to trace our angle alpha through this picture. That's going to kind of be one of the requirements of our proof. So let's introduce some maybe color notation here. Let's say our angle alpha is in yellow, and then the complement of our angle alpha, 90 minus alpha, will be in blue. Now let's do this in stages. So we're given this right here is angle alpha. And then here, this is a right angle. Well, by the angle sum of a triangle is 180 degrees, we know this angle right here has got to be the complement of alpha. So we've got that. But then this angle AQR is a right angle. So that makes, let's see, OQR the complement of alpha. In other words, that's going to be alpha again. Okay, so we know that that angle is alpha. Then, well, where can we go from there? So now we know that this angle is a right angle. Here's the complement of the yellow, which is going to be the blue again. Okay, so we've got this is a blue angle. And then finally, we get alpha and maybe its final location for our purposes, and that would be up here. So this is also angle measure alpha, because again, the angle sum of a triangle is 180 degrees. And so we know blue plus yellow is equal to 90 in our color coding setup. Okay, So now that we've got all of these parts, we're just pretty much ready to let it rip. So let's observe that the sine of alpha plus beta can be calculated via this kind of triangle OBP. So it'll be PB or BP over PO. Remember, it's going to be the opposite over the hypotenuse. But I'm going to break BP up into BR and then RP. So that's going to give us BR over PO plus, like I said, RP over PO. So something like that. Now let's observe that since we have a rectangle right here, ABRQ, side length BR is the same length as side length AQ. So I'm going to go ahead and make that change. So I'll take this BR and I'll replace it with AQ. Now I'm going to take each of those components over there and essentially multiply them by 1 and rewrite it. So what's that going to look like? Well, my first one is going to be AQ over OQ times OQ over PO. Again, I just multiplied by OQ over OQ, so the length of that line segment OQ. Now I'm going to do the same thing in this next one, but now it'll be QP. So here we'll have RP over QP times QP over PO. So we've got something like that. And now we really just want to look at all of those ratios and write them as trig functions. So let's see, AQ, so where is that? AQ over OQ, so that's going to be the sine of alpha. So here we have the sine of alpha for this first term. And then next up, what do we have? Well, we're going to have OQ over PO. We'll observe that's going to be the cosine of beta built out of this triangle. So we have the cosine of beta right there. And I guess like we could have used these values that we figured out already, but it's not too bad to just work through it again. Now let's look at the other part. So this is going to be RP. So let's find RP over QP. Well, observe that uses this triangle up here that we built with our angle alpha by chasing the angle through here. And you can see that that's going to be the cosine of alpha. And then finally the QP over PO. So QP over, let's see, where is it? PO, well, that's going to be the sine of beta by a similar argument. So here we have, this is the sine of beta. But observe, like starting over here and ending over there, we get kind of the well-known angle sum formula for sine. Now you can play the same kind of game to get the angle sum formula for cosine. I'm not going to do that here, but needless to say, it's a very similar argument. Okay, so now that we've got our angle sum formula, since we're looking at most of the details here, let's go ahead and calculate the derivative of sine. Thanks for sticking around this long into the video. If you're enjoying it, make sure and give a thumbs up, and if you're not yet subscribed, consider subscribing, it really helps out. Okay, so we just did a geometric argument of our angle sum formula for sine, and the one with cosine is similar. Now what I'd like to do is use that angle sum formula to calculate the derivative of the sine function. So here we're going to use the limit definition. So we've got the limit as h goes to 0, and then our sine of x plus h minus sine of x all over h. So let's see, that's going to give us this limit as h goes to 0 of, so now what goes in that numerator? Well, we're going to use that angle sum formula there. So that'll be the sine of x times the cosine of h, and then plus the cosine of x times the sine of h minus the sine of x all over h. So we've got something like that going on. So now what I'll do is I'll do a little bit of grouping here. So let's group these two that I'm overlining in green and factor the sine of x out. So that's going to give us the limit as h goes to 0 of, so we'll have sine of x and then the cosine of h minus 1 over h. So that's what we get after factoring that sine out. And then we'll have the cosine of x times the sine of h over h. And now we're left with some limits that may or may not be familiar, but we're going to maybe assume that we've seen them before, and that is this cosine h minus 1 over h and sine h over h as h approaches 0. Now, you can do a nice geometric argument to prove these two values, but we'll skip that. We want to be thorough, but maybe not too thorough. So let's see. This tends towards 0 as h tends towards 0, and then this sine of h over h tends towards 1. So in the end, we'll get that this is the cosine of x. And then likewise, you can get that the derivative of cosine is negative sine. Okay, so now that we have motivated the fact that we can prove lots of these things about the sine and cosine function, like the derivatives and all that kind of stuff, without the Pythagorean theorem, let's jump to having their Taylor series, which only involves needing the derivative. It doesn't involve needing the Pythagorean theorem. And then we'll use their Taylor series to gain this formula right here. Okay, so using the derivative, we can gain the Taylor or Maclaurin series expansion for sine and cosine. Now here I've written them just with these unknown coefficients Sn over n factorial and Cn over n factorial. So these are technically the exponential generating functions for the sine and the cosine. But that being said, what we want to do is use the fact that we kind of know what these are, but we'd like to write those numbers, Sn and Cn, in a clever way. So I'd like to recall that Sn will be defined as follows. So we have at even values, it's 0. And then at odd values, S2m plus 1, you get minus 1 to the m. So that'll give you your standard maybe Taylor series or Maclaurin series for the cosine function. Then you can do the same thing for the cosine function. So here we have C2m is equal to minus 1 to the m. So the even values alternate like that. And then the odd ones are all 0. So again, that's well-known facts. Now what I'd like to do is push these two things together in each of these cases, the sine case and the cosine case, to get maybe a single formula. So here's what we'll do. We'll observe that this is equivalent to setting Sn equal to 1/2, and then I to the power n minus 1 plus I to the power 1 minus n. So I'll let you check that out in all of the details if you want to, but maybe down here, I'll just check that it works for the even values. So let's observe that S2m here will be equal to 1/2, and then we'll have I to the 2m times I to the minus 1. There I'm using just exponent rules. And then this will be plus I times I to the minus 2m. But observe that I to the minus 2m is going to be the same thing as I to the 2m. They're both equal to minus 1 to the m. So actually, let's write that out here. This is minus 1 to the m. This is also minus 1 to the m. That's because I squares to minus 1. But now what we can do is observe that I inverse is simply equal to minus I. That's because minus I times I is 1. But now observe we've got the same number times minus I plus the same number times positive I. So of course this is going to become 0. So again, that's just a gut check that that works for even inputs of this sequence S, but you can check for the odd inputs as well. Now, what about this sequence C? Well, it's going to be fairly similar. Here we'll have Cn is equal to 1/2, and then I to the n plus I to the minus n. And you can do your same checks just like this right here, that you get 0 when you need to, and you'll get minus 1 to the m when you need to. Maybe we'll do the C2m, the even ones again. So that'll be 1/2, and then we get I to the 2m plus I to the minus 2m. But in both of those cases, we get minus 1 to the m power. Those are going to clearly add together to 2 times minus 1 to the m power, but we've got this half out front, so we get minus 1 to the m power. So we're left with something like that. All right, so now that we've taken care of this, what I'd like to do is see how this maybe expression helps us with our calculation. So now we need to calculate the sine squared and the cosine squared using maybe this general formula right here with these s coefficients and these c coefficients. Later, we'll use the fact that we know what they are. Okay, so let's first calculate sine squared of x, and this is going to be using the convolution formula for multiplying infinite series, or really just series in general. So this is going to give you the following. So the sum is n goes from 0 to infinity, and then after that, it'll be the sum as k goes from 0 to n of s sub k times s sub n minus k over k factorial times n minus k factorial, and then we have an x to the n out here. So again, that's the standard formula for multiplying series. I'll let you guys check that out if you need to. Okay, so now where are we going to go from here? Well, what I'd like to do is take an n factorial, multiply it in the denominator right there, and then likewise multiply it in the numerator right there. But then if we multiply it in the numerator, observe that we've just built a binomial coefficient. So that's going to give us the following. So I'm going to write this as the sum as n goes from 0 to infinity. And now inside of that sum, we have this sum as k goes from 0 to n of our binomial coefficient n choose k. And then we have sk sn minus k. And then we have x to the n over n factorial in the back half. Now we can do a very, very similar calculation to see that cosine squared is going to be equal to the sum as n goes from 0 to infinity of the sum as k goes from 0 to infinity of n choose k, and then we've got ck, and then cn minus k, and then x to the n over n factorial. So that's where we're left off with now. Okay, so next up what I'd like to do is maybe start the final calculation involving series, which will lead us to a nice combinatorial argument at the end. So before we start finishing everything off, I'd like to tell you about my second channel math major, which includes full lecture courses in mostly upper division math classes. I think I have about half a dozen classes, and these are all ad-free thanks to my support on Patreon and channel memberships. If you'd like to help us out maintaining this ad-free content, maybe think about becoming a patron or joining channel memberships, although there's no pressure. Okay, so here's where we left off. I pushed those two sums together, and observe we've got this object to deal with right here, which is this sk sn minus k plus ck times cn minus k. So let's maybe just bring that blue underline over here to this blue square, and that'll be what we work with now. So sk sn minus k, and like I said, plus ck, and then cn minus k. And so recall that each of these had a format, right? So this sk was, for instance, let's write it down. It was 1/2, and then it was going to be I to the k minus 1 plus I to the 1 minus k. And there was a similar formula for Sn minus k. Well, our Sn definition will give us all of these. And so similarly for the ck definition. But what's really involved here is just expanding everything out and then recombining. So I'll just maybe skip some of that arithmetic, and here's what we're left with. So we've got 1/4, and then we'll have I to the 2 minus n. I'm not doing any simplification just yet. Plus I to the power 2k minus n. And then plus I to the power, let's see, n minus 2, and then plus I to the power n minus 2k. And just maybe if you're interested, this is our sk term. So that's the product of those two sk terms. And then we're going to add that to the product of the two ck terms, and that's going to give us this. I to the 2k minus n, and then plus I to the minus n, and then plus I to the n, and then finally plus I to the minus 2k plus n. So I guess that's n minus 2k. So we've got something like that. And just to be really thorough, let's underline that in green, and that's where that's coming from. But let's observe that we get some simplification. Some of these things are kind of obviously opposites of each other. So observe that this is really equal to minus 1 times I to the minus n, so that's going to cancel this term right here. And then likewise, we've got one more, and that would be this I to the n minus 2, and then this I to the n. Because I to the n minus 2 is going to be I squared times I to the n. Or really like I to the n over I squared, but that's just minus I to the n any way you look at it. So next up, I think we've got some like terms as well. So this term right here is the same as this term right here. And then similarly, this term right here is the same as this term right here. So that means we can maybe push those together and then we'll have a half in front of everything. So let's see what that's going to give us. That's going to give us an I to the 2k over 2, and then we'll have I to the n plus I to the minus n. Now what I'd like to observe, and this is fairly obvious, and that is that this I to the 2k is really I squared to the k, or minus 1 to the k. So that gives us something like that. That's quite a bit simpler. Now what I'd like to do is take this expression for this sum of s and c type terms, and I'll insert it into our formula up there. All right, so this is where we left off. Now I'd like to make an observation about this I to the n plus I to the minus n over 2 type term. And let's observe that this is equal to 0 if n is odd. I think that's pretty easy to see. And then this is equal to minus 1 to the n over 2 if n is even. Again, that's not so hard to see either. So what does that leave us with? Well, now we can only keep the even terms, and by only keeping the even terms, we can re-index this thing, replacing n with 2n, and that's going to give us this sum as n goes from 0 up to infinity of minus 1 to the n. And then here we have the sum as k goes from 0 to 2n of minus 1 to the k, and then 2n choose k. And then we've got x to the n over n factorial. So we're left with something like that. Now, I'd like to observe that if you set n equal to 0, everything simplifies down just to the number 1. So that's a pretty easy calculation. Let's skip that. So here we can put a plus 1 here, and then start this at n equals 1. Now I'd like to write this as 1 plus the sum as n goes from 1 to infinity, and then this minus 1 to the n over n factorial times x to the n. I'm going to reorder things a little bit. And then inside of that, we'll have the sum over even k, and that's going up to 2n, of 2n choose 2k minus the sum over the odd k up to 2n of 2n choose k. So of course, you can do that. You can always just split your sum up into even and odd parts, keeping in mind because of this minus 1 to the k, that'll give us a plus in front of one and a minus in front of the other. But now I'd like to introduce some notation, and this notation may not seem super useful at first, but it in fact will be useful. Let's say that s sub even is equal to the number, or sorry, not the number, the set of subsets of the set 1 up to 2n with even number of elements. So let's say that n is equal to 2, for instance. So that's going to be the number of the set of subsets of the set containing 1, 2 with only an even number of elements. So that would include the empty set, and that would also include the whole set. So that's the only way to get an even number of elements there. And then we'll set s sub odd equal to the same thing. So I'll just put a line here. That's the same thing with even exchanged for odd. So in our n equals 1 case, which is the set containing 1, 2, that would give us the singleton 1 and the singleton 2. So that means I can take this portion of our sum and replace it with s sub even, really the cardinality of s sub even minus the cardinality of s sub odd. And now we're ready to pretty much finish this thing off. So I'd like to define the following function. And this comes from the power set of the set from 1 to 2n back to the power set of the set containing 1 to 2n. So that's the set of all subsets. And what I'll do is I'll define its action as follows. So f evaluated at a subset A is going to be equal to A union 1 if 1 is not an element of A. So if 1 is not an element of A, it sticks it inside of A, or it sticks it inside the image. And then it's going to be A set minus the singleton 1 if 1 is an element of A. So it puts A inside of the image or the target, and it takes A out of the target depending on if it's in or out. Now I'd like to observe the following, and you can check this. So, and that is f is injective. So this is a one-to-one function. And then furthermore, f of s even equals s odd, and f of s odd equals s even. But that tells us that s even and s odd are the same thing. But that means that this difference right here is equal to 0. But then if that difference is equal to 0, what's the only thing that remains in this big calculation? Well, it's in fact exactly what we want to remain. We have this sine squared plus cosine squared equals 1. But as we discussed at the very beginning of the video, that is equivalent to our Pythagorean theorem. And that's a good place to stop.